Hello everyone, welcome to my talk. Today I'm going to be talking about my paper, RVPLAYER, Robotic Vehicle Forensics by Replay with What If Reasoning. I'm Hongjun Choi from Purdue University. As we know, the robotic vehicles are becoming more and more popular these days. They are used for various applications, including package delivery and passenger transport, and military drones and RVs for underwater and space exploration. All these vehicles are safety critical, and the failure of the systems causes physical damage and even threatens human lives. However, we have been observing a lot of accidents of autonomous vehicles for various reasons, such as human factors and erroneous control commands and unknown software glitches. Moreover, with the popularity of autonomous vehicles, the number of accidents will be increasing more and more. So after-attack investigation to analyze the root cause of the accidents is particularly important in this context. On the other hand, such incidents may be caused by cyber and physical attacks. Actually, Iran hijacked the US military spy drone in 2011, and hackers remotely controlled the vehicle by exploiting a vulnerability of the entertainment system in the car. Even worse, some vulnerabilities and attack tools for the commercial drones are already available on the internet. So the after-accident investigation or forensics will be more challenging under such advanced cyber and physical attacks. Let me give you an example of advanced attack scenario to motivate our technique. This example illustrates the stealthy, multi-stage, and long-time attack on a drone with malicious control parameter update. Here is a drone, and the operator can issue multiple commands to update control input, such as control parameters and missions, through the ground control system remotely. Given the planned trajectory for a long-time operation, let's say the several days, the drone may encounter different types of external disturbances. Some of them may directly affect the physical maneuver of the drone, and some of them are not. While the drone flies, the normal operator can update benign parameter or mission, but attacker also can pretend a normal user and update the malicious parameter with a small footprint. Here, the parameter lower gain is responsible for the lower control. The malicious large value leads to the overshot of the actuation signal for lower control during significant load changes, such as sharp turn. However, during the straight flight or the mild turn, there will be no significant impact. So at this time, the malicious update remain hidden for long operation time until triggering conditions are satisfied. So after the long simple operations, when the drone makes a planned sharp turn under a wind gust, the malicious behavior is finally triggered. So the significant overshot for lower control boosted by the sharp turn and wind gust actually causes the control error and the crash. In this scenario, it would be challenging to identify the root cause of the crash because the malicious activity happened long time before the actual crash, and there are so many factors to need to be investigated. So the simple and naive investigation may determine it is a natural accident due to the sharp turn under a wind gust, not an attack. However, as we know, the actual root cause is the effect of the malicious parameter being maximized by the aggressive lateral movement under harsh environmental conditions. So the combination of all these factors actually caused the accident. To analyze the root cause, we need to investigate all the past cyber events and physical states for the long time operation, various types of the external disturbances and their combinations. So for efficient and effective analysis, we need to address several practical challenges. Challenge 1, how to measure all the non-deterministic external disturbances. The vehicle may need to equip a large number of physical sensors, but that is not practical. Second, we need to maintain such heavy flight data for long period of time, considering resource constraints in RV system. And lastly, we need to support a systematic method to identify the root cause of the attack based on these recorded log. So we developed RVPLAYER, an efficient replay-based forensic framework which allows to reproduce accidents and reason about its causation. Here is an overview of our technique. It has two main components: on-the-fly logging and offline after-accident analysis. Our on-the-fly logging is efficient and innovative, which addresses the challenge 1 and 2. And our disturbance observer inserted in the system leverages the vehicle's dynamics model and estimates the aggregate effect of external disturbances without using dedicated sensor for different physical properties. Our adaptive logging technique reduces log size significantly by selectively recording abnormal physical state information based on the dynamics model, and it reduces log size by 90% in our experiments. With the runtime logs, our offline analyzer systematically locates the root cause of the accident, which addresses challenge 3. Our replayer reproduces the accident in simulation with the vehicle's dynamics model, and during replay, it changes recorded factors such as cyber and physical events with external disturbances, and then observe consequences to see which factors actually contribute to the accident. Our replayer supports various replay policies that modifies input configuration for different type of attack. Let me explain the key idea in each component in the next slide. So as I mentioned before, measuring and recording various disturbances such as wind, temperature, and aerodynamics effects, and so on, it requires a lot of designated and special physical sensors, which is practically infeasible. So disturbance observer, it is a widely used robust control methodology, and the role of our observer is to estimate aggregated effect of the external forces with a predictive model that is derived by the gray box system identification. So it can decouple and record external disturbances without various dedicated sensors. Okay, let me explain how we can estimate external forces conceptually. Here the drone tries to keep the balance. So the sum of thrust forces by the motors and the gravitational forces is 0. Later there is no disturbances. The forces remain the same because we don't have additional external forces, and the physical state and the model prediction are the same, maintaining a balance. However, when we have a strong wind in this direction, the drones try to keep the balance by increasing motor thrust on the right. Otherwise, it will be tilted to the right because of the wind force. But the model does not include the wind force, and the only increased thrust is applied, which makes the drone tilted to the left. So by measuring the state difference in acceleration from the real-end model, we can estimate and decouple the external forces, in this case wind force. This external disturbance is separated and recorded, and later applied one of the physical events during replay. Another key feature is adaptive logging. Considering runtime and storage constraints, we reduce the log size by adjusting the logging frequency based on the anomalies of current physical state. The key observation is that the normal operation, excluding the disturbances, are mostly nominal and accurately predictable and reproducible. So we don't need to record such normal physical states, and only record unusual state and disturbances with high frequency. Here is a trace of state X over time, As you can see, the real state in black line is significantly deviate from the predicted state between T1 and T2. So we increase the logging frequency in this period to record the abnormal state in high frequency. The logging frequency f is determined by this equation. Intuitively, the frequency is adjusted at runtime based on the degree of anomaly. So this is very innovative because during offline replay, we can reproduce the missing nominal states by our model. So we save a lot of and huge amount of storage. The state between T1 and T2 is reproduced from the log, and the last of the part, that is a normal state, can be reproduced by the predictive model. So we can reproduce the complete trace offline. Next, I will explain how to investigate the tag. So in order to identify root cause, our technique performs the multiple replays with what-if reasoning. Here is a previous example. So for each explanation, I abstracted the cyber events with the symbol C and disturbances with D. First, we simply play with the initial configuration by applying all the factors recorded in the log, C and D, without change, which will reproduce the original error, original accident. Then, given the initial configuration from the entire factors, we mutate it by randomly selecting some of them to disable during replay. So when the replay will change, successfully suppress the original accident, we can determine the set of disabled element includes the root cause. But it could be the superset that includes the other factors as well. So we keep searching to find the configuration that has minimum factors, minimum number of disabled elements that can suppress the accident. So this process actually requires a lot of replay runs. So we utilize meta-heuristic search method, genetic algorithm. So the quality of individuals during selection operation is measured by distance from initial configuration. We evaluate our technique with the various target systems and attacks. In total, we use 6 RVs and 5 real-world auto-driving traces. We use real-world missions in an urban area with diverse errors, such as GPS signal loss, wind, different temperature, and so on. And performance, our log reduction rate is over 90% with the adaptive logging technique for various missions and environment conditions over our multiple targets. And we have a small runtime error, which is at most around 7% in our target system. We also report how accurately our technique reproduces the original traces. The average position error of RVPLAYER is less than 0.7 meters across all target vehicles, and the figure on the right side shows the comparison between the original physical states and the replayed traces for different physical states during the real complex mission of 3DR solo drone. The errors are very small. So lastly, we evaluate our technique on 5 types of attacks. These attacks are all from the recent CPS security paper as shown below, and we tested a total of over 1,000 attack instances of these various kinds, and RVPLAYER can accurately identify all the root causes. So we additionally report detailed results such as number of replay runs and total replay time, identify root cause, and so on. In addition, the case studies and demo videos are available in our paper and the project webpage. So we introduced RVPLAYER, which is a novel forensics analysis technique for RVs. It captures environmental disturbances at runtime and replays to reconstruct the actual attack traces offline. Our adaptive logging and what-if analysis technique allows us to efficiently and effectively analyze the root cause of the attack and accidents. Thank you for your attention.